We've already seen that gases consist of individual atoms or molecules that are separated by mostly empty space, except for the occasional collision with each other or with a wall. But at low temperatures or high pressures, all gases will condense into a liquid or solid. The temperature at which this occurs depends on the strength of attractive interactions between the molecules. The weakest type of interaction is called the dispersion force, or London force, after the German physicist Fritz London, who explained it in 1930. The electron cloud around every atom or molecule constantly undergoes random fluctuations, which generate a small transient dipole moment. This dipole is felt by the electron clouds of nearby atoms, which can lower their energy by generating a small dipole that creates an attractive interaction. It is this correlated motion of these electron clouds that creates the attractive forces between molecules. The forces are small, except in very large molecules, but all atoms and molecules have electron clouds, so this type of interaction is universal. Attractive interactions can be somewhat stronger if the molecules have a permanent dipole moment. This happens when compounds include atoms with different electronegativities, like carbon monoxide. This stronger interaction induces at least a small amount of alignment and structure in the liquid or solid as the molecules arrange their positions to take advantage of the favorable dipole interactions. Symmetrical molecules like carbon dioxide and benzene do not have a net dipole moment, but have weaker quadrupole moments instead. When a molecule contains hydrogen bound to a strongly electronegative atom like fluorine, oxygen, chlorine, or even nitrogen, the H atom on one molecule can form a partial chemical bond to the electronegative atom on another molecule. This hydrogen bonding interaction is especially prevalent in water because each O atom can be strongly bound to two H atoms and weakly bonded to two others. So even though water is a very small molecule, it remains a liquid at room temperature and has a surprisingly high boiling point of 100 degrees Celsius. Compare this to methane, which is larger but boils at minus 162 Celsius. Metals are held together by strong chemical bonds, but unlike covalent compounds, the bonds are not usually formed by sharing a single pair of electrons. Instead, you can think of most metals as an ordered array of cations embedded in a delocalized sea of valence electrons that flow freely between the cations. This structure allows metals to be flexible and ductile, making them very useful as structural materials. The electrons reflect light, making metals shiny in appearance, and the free flow of electrons allows metals to be good electrical conductors. In ionic compounds, both the cations and the anions occupy positions in an ordered lattice that takes advantage of delocalized attractive interactions. These materials are almost always solids at room temperature and have extremely low vapor pressures. Materials like silicon and diamond can form a three-dimensional network of strong covalent bonds. As a result, diamond is the hardest material known, and synthetic diamonds are widely used for industrial drills and saws. The properties of liquids are dominated by the strength of intermolecular interactions. When the cohesive forces are strong, it can cause liquids to have a high viscosity, like molasses or motor oil, especially at low temperatures. Surface tension is the result of molecules at the surface of a liquid having access to only about half of the normal cohesive forces. As a result, liquids will modify their shape to minimize their own surface area, adopting a spherical shape for droplets, and combining small droplets into larger ones wherever possible. In cases where cohesive forces between liquid molecules are stronger than adhesive forces to other materials, the liquid seeks to minimize the contact area. However, sometimes the adhesive forces can be strong, which results in the liquid wetting the surface and flowing over much of it. The interaction of cohesive and adhesive forces is exhibited in the phenomenon of capillary rise. The height to which a liquid will rise against the force of gravity depends on the surface tension, T, as well as the contact angle, theta, between the liquid and the solid. The contact angle between mercury and glass is unusually large, so the cosine of theta is negative. This actually results in a depression of the surface inside the capillary tube. Capillary flow is responsible for the absorbency of paper towels and the ability of trees to carry water from the soil up hundreds of feet to the branches and leaves to carry out photosynthesis. Almost all substances can undergo transitions between liquid, solid, and gas phases. The names of these transitions are shown in the figure here. Usually, there is only one stable phase for any combination of temperature and pressure. However, at the melting point, a liquid and a solid may coexist in equilibrium, or a solid and a gas may coexist at the boiling point. When two phases exist in equilibrium, it means that their overall chemical potential energies are identical. However, there may be a substantial difference in enthalpy, meaning that even at the boiling point, you must add lots of heat to convert liquid water into vapor. This is why water boils at a constant temperature of 100 degrees Celsius. Even at temperatures below the boiling point, most liquids exhibit a significant vapor pressure because a small fraction of molecules at the surface have enough kinetic energy to escape the cohesive forces and jump into the gas phase. At the same time, gas phase molecules are easily captured by the liquid. This constant competition between vaporization and condensation results in an equilibrium vapor pressure of the compound above the liquid surface in a closed container. Because the Boltzmann distribution of kinetic energies is a strong function of temperature, the vapor pressure of a liquid usually increases sharply with temperature, according to the equation shown here. If we compare the vapor pressures at any two temperatures, we can see that this ratio depends on the enthalpy of vaporization of the liquid. The second equation here is called the Clapeyron equation, and it allows us to estimate the vapor pressure of any liquid at any temperature using the boiling point and the enthalpy of vaporization. Phase diagrams are useful for visualizing the relationships between solid, liquid, and vapor phases as a function of temperature and pressure. Look at the horizontal red line at 100 kPa or 1 bar. At temperatures below 0 degrees Celsius, water is a solid, and between 0 and 100 degrees Celsius, it's a liquid. Above 100 degrees Celsius, it turns into vapor or gas. But if we raise the pressure, for example in a pressure cooker, we can raise the boiling point, where liquid and gas coexist in equilibrium. And this makes food cook faster. Following this liquid-gas curve to higher temperatures, the enthalpy of vaporization decreases and eventually becomes zero at the critical point at 647 kelvins. Here, the difference between gas and liquid disappears, and above this temperature and pressure, we call it a supercritical fluid. Water has a very steep liquid-solid curve, and its slope is negative, meaning that the melting point decreases slightly with increasing pressure. This is quite unusual, and it gives rise to the ability to use ice skates to glide on the surface of ice. This more detailed phase diagram for water shows that although substances have only one liquid phase and one gas phase, they may have many different solid phases, each with its own characteristic crystal structure. This is the simplified phase diagram for carbon dioxide, which exhibits the usual positive slope of the liquid-solid curve. The triple point at 216 kelvins and 5.17 bar is the only point on the diagram where solid, liquid, and gas can coexist in equilibrium. What is somewhat unusual is that this triple point lies above a pressure of 1 bar. So liquid CO2 does not exist at ambient atmospheric pressure. Therefore, if you purchase dry ice, you can observe it change from the solid directly to the vapor without ever melting. In the region above the critical point, supercritical CO2 is an excellent solvent, and it's used commercially for extracting caffeine from coffee beans to make decaf coffee. Solid substances fall into two broad categories: amorphous solids, which have no long-range order, and crystalline materials, in which the local molecular structure is replicated across the entire macroscopic crystal. Silica, which is the major component of glass, is a good example of an amorphous material. The local structure is well defined, with each oxygen atom being bound to 2 silicon atoms, and vice versa. However, the random nature of the ring sizes, shapes, and orientations destroys any structure beyond a few nanometers. As a result, the material appears to be homogeneous on a scale of the wavelength of visible light, and glass appears to be clear, as in Dale Chihuly's glass sculpture shown here. Crystals, on the other hand, are formed when molecules arrange themselves in one of 14 different unit cells that can be replicated millions of times, filling a macroscopic three-dimensional space. The structure of crystalline compounds is most often solved using X-ray diffraction. The regular arrangement of atoms in planes causes a collimated X-ray beam to be diffracted, creating spots of intensity as shown here through constructive and destructive interference of the waves. The Bragg diffraction equation states that for constructive interference to take place, the difference in path length between two interfering waves must be equal to an integer multiple of wavelengths. This allows the spacing between atomic planes to be determined by measuring the diffraction angle, theta. Of course, for complex materials like proteins, many calculations are required to determine all of the bond lengths and angles in the molecule. The properties of liquids and solids are much more complicated than simple gases, but the importance of understanding intermolecular interactions is underscored by the fact that almost everything in our world is made of condensed matter, except the air that we breathe. And after all, 3/4 of the surface of our planet is covered by water, which is an essential component of all living things.